Good morning, I am Renu Sharma, Assistant Professor EC Department. Today I am going to start with the next lecture of Unit 3rd, and today's lecture will going to cover the topics that are spread spectrum modulation, that is also known as SS modulation. Then we are going to use the pseudo-noise codes with properties, that is also in short it is known as PN codes, and code generation mechanism. Then two different types of SS modulation, four different types of SS modulations are there. Like first one is the DSSS, then FHSS, time hopping, and hybrid spread system. So these are the four different types of SS modulation. So SS modulation, it is a technique that by which a signal generated with a particular bandwidth is deliberately spread in frequency domain, resulting in a signal with wider bandwidth. So what we are going to do in spread spectrum modulation, as the name itself is self-explanatory, spread spectrum means in the frequency domain we have to spread the spectrum. And how we are going to do it? Like it is used to modulate a signal. Let's say we are having 4 different bits like 1, 0, 1, 1, and we want to modulate using this SS modulation. Then a modulo 2 addition will be performed through this PN sequence. This PN sequence is nothing, it is, let's say it is 15 bits of code, 18 bits of code, so which will be much higher length as compared to this 4 bit of data. So 15 bit of length will be modulo 2 added using this one, and then we are having this spread spectrum modulation. So this is how this SS modulation will going to work, and the output will be a spread spectrum modulation. So these techniques are used to for a variety of reasons, including the establishment of secure communication. So basically the transmitter used to perform this spreading, and that is known as encryption also. Encryption is based on this SS modulation, and whatever PN sequence, let's say it is of 15 bits, so whatever PN sequence we have used at the transmitter side, the same PN sequence has to be used at the receiver side. Then only the data will be decrypted, then only you are going to get this 1011 actual information. Otherwise the demodulation will not work properly, and there will be noise which will going to affect the quality of the signal. So these techniques are used for a variety of reasons. Let's say it is used for the secure communication. It increases the resistance to natural interference, noise, and jamming, to prevent detection and to limit the power flux density. Then to achieve these goals, spread spectrum techniques are will going to add the redundancy. They spread the original spectrum needed for each station. Then if the required bandwidth for each of the station is denoted as B. Now you can see over here, like this is the input signal which is applied to this spreading process, and the spreading code will be there. Now this code is nothing, it is the PN code or the pseudo random code. Now this 15-bit code is randomly generated code. It is not fixed every time you are going to generate the PN code. So the output will be the bandwidth extension of this one, and then we are getting this spreaded code that is denoted by this BSS. Now you can clearly see that the bandwidth of this spreaded code will be quite large as compared to the bandwidth of the original signal. Now the expanded bandwidth allows the source to wrap its message into a protective envelope for a more secure transmission. So after the signal is created by the source, the spreading process uses a spreading code, and then it will going to spread the bandwidth of the signal. Now next one will be the pseudo-noise PN codes with its properties and code generation, how it will be going to generate the code. So assume that a clock rate is provided for generation each bit of a PN code with 1 clock cycle, and 1 bit of PN code comes out. So basically for the 1 clock cycle, the 1 bit PN code will be generated. So for n number of clock cycles, n number of bits will be generated in the PN code. Now the bit rate of a PN code is called as the chip rate, that is denoted by 1 upon TCP, so which is 10 times more than the data rate. So you can imagine that, let's say 1 bit of data is the actual data, then 10 bits we are taking as an PN code. So this is the rate of generation of the PN code. It should have a larger bandwidth as compared to the input data, then only the encryption or the security of the information will be done. Now the smallest time increment in the sequence of certain period or duration is T chip and is known as the time chip. Then the total period consists of NC times the chips. Now the chip rate decides the final transmission spectrum of the DSSS system. Several spreading codes are popular for the use in practical SS systems. So some of the codes are the maximal sequence code, that is known as M sequence. Then gold codes are there, Kasami codes are there, then Barker code. So these are some of the examples of PN codes, that how you are going to generate the M sequence code. Now these are the longest code that can be generated by a shift register of a specific length, say its length is L. Now at an L stage shift register and a few XOR gates can be used to generate an M sequence of length 2 to the power L minus 1 basically. So this is how the data will be generated in the PN sequence. Now next is the maximal length pseudo random code generator. So this is how the code will be generated. Now you can see that n number of registers are there, like this is the first register, that is basically a 1 bit register. Register is a 1 bit storage unit. Then this is the second register. So up to n points we have used n number of registers are there. Now modulo 2 addition is applied to the last 2 registers, so likewise the modulo 2 addition will be there, and clock will be required for the operation of each register. So this figure shows the M sequence generator using an n memory element such as flip-flop. So if we can we keep on clocking such a sequence generator, the sequence will going to repeat, but after 2 to the power L minus 1 number of bits. So the number of 1 minus S is in the complete sequence, and the number of zeros in the will going to differ by 1. So if L is equals to 8, then it will be generated the 128 ones and 127 zeros will be there in the complete cycle of the sequence. So this is how the data will be generated. So if the period of M sequence is n chip, then n is equals to 2 to the power n minus 1, where n is the number of stages in the code generator. So using this n registers in a row, how the code will be generated, which is of M length. So this is the diagram is explaining this particular generation of bits. Now next one is the autocorrelation property of the PN sequence. So autocorrelation is basically when 2 codes are generated, we have to see that what is the correlation between 2 bits. Now autocorrelation and cross correlation, 2 things are there. Autocorrelation is seeing the correlation between the data and its shifted version by itself, and in case of cross correlation, 2 different datas are considered and the correlation between them will be checked. So there is a correlation coefficient exists that has value -1, 0 and 1. -1 means it is correlated with each other, but in the negative sense, means opposite to each other, but they are correlated. 0 means they are neither the 2 codes are not correlated to each other in any sense, and positive 1 means the both sequences are correlated, they are exactly same. So this is the diagram. The autocorrelation should be maximal for the DS or the PN codes so that the current PN sequence can be identified at the receiver from the numerous coexisting signals. So you can see that this is the autocorrelation of the PN code that will vary from -T chip to +T chip, and this is the length of this particular code. So autocorrelation, cross correlation equations are shown over here, that is 1 upon T code. That will vary from 0 to infinite Ct to Ct plus tau dt. So this is T code is equals to NC T chip, which is the code period, and tau represents a time shift variable. Now there are two different types of spread spectrum system. Like first one is the averaging system, second one is the avoiding system. Now in case of this averaging system, the interference reduction takes place because the interference can be averaged over a large time interval. So this is how the averaging will be made of all the sequences that have been generated. In case of this avoidance system, the reduction of interference occurs because the signal is made to avoid the interference for a large fraction of time. So there is a frequency hopping, time hopping, and chirping system will be there. So all the other there are four different types of SS modulation: DSS, direct sequence, frequency hopping, time hopping, and a hybrid system. So direct sequence will be a part of averaging system, and avoidance system undergoes this frequency hopping, time hopping, and chirping system. Now next one is the direct sequence spread spectrum, that is DSS system. In this system, these are also expands the bandwidth of the original signal, but the process is different. In this DSS, each data bit is replaced with n bits of data using a spreading code. In other words, each bit is assigned a code of n bits called the chips, and where the chip rate is n times that of the data bit. So DSS constitute this particular data. So whenever a user wants to send the data using this DSS technique, each and every bit of the user data is multiplied by a secret code that is known as a chipping code. Then the receiver uses the same code to retrieve the original message, that is the direct sequence spread spectrum technique. Now this is the diagram which is showing that how this DSS will going to work. This is the original signal, this is the modulator data. Then the chip generator will be applied to this. The output of this will be a spread signal. Now this spread signal is applied as an input. You can see that this is the original data and this is the bit rate. You can see that in one bit you have transmitted this 1, 2, 6, 7, 8, 9, 10, 11. So 11 bits you are considering as a spreading code corresponding to the 1 bit of original data, and this will be the spread signal. So basically you have applied a modular 2 addition between these 2 points and you are getting as an output as an spread signal. So this is the direct sequence spread spectrum technique. So this is the transmitter and the receiver diagram. Like this is the transmitter part, user data will be there. The chipping sequence, that is nothing, it is the PN sequence that is applied as an input to this one. The output will be a spread spectrum signal. Then it is applied to a modulator, and then to a modulator we require a radio carrier, and then transmit signal will be generated, the data that you want to transmit. Now whatever you have transmitted over the channel, it will be received at the receiver side. This is the received signal. Then it is passed through a demodulator. To this demodulator again we require a carrier signal. So whatever carrier signal you have used at the modulator, the same carrier signal has to be used at the demodulator side for the purpose of maintaining the synchronization. So at the output of this one, the chipping sequence will be generated. Now this is applied to a correlator, and the output of this one, there will be a decision device and a data will be generated. So whatever data you have transmit over here at the receiver side, you are going to get that particular data if you have used the same chip sequence and same carrier signal at the transmitter and receiver side both. Now next one is the frequency hopping spread spectrum, FHSS. So the technique uses m different carrier frequencies that are modulated by the source signal. So at one moment the signal modulates one carrier frequency, at the next moment the signal modulates the another carrier frequency. So you can see that the bandwidth of this particular signal is far greater than the bandwidth of the actual signal. So you can see that it is the diagram which is being drawn between this time, frequency and power. So this is the time. You can see that it will going to hop in different frequency range. So this is the FHSS diagram. Now this is the diagram of transmitter and how the data will be generated. In this case, the original data is applied to the modulator. To this modulator, we require to apply a pseudo random generator. Now, this particular output is not directly applied through this one. It is applied through a frequency table. It applied through this frequency synthesizer, and the output you are getting this spread signal. So, this is the first hop frequency. This is the frequency table. which is of k bit of data, and this is the frequency range, that is 200 or 300 hertz and up to 900 kilohertz of frequency. Now this is the k bit pattern, and the frequency selection will be there. So whatever pattern you are going to select over here, you are getting as an output over here. Now next is the pattern for this station is 101, then 111. So you can see in this particular table the patterns are written over here, and you are going to use that corresponding frequency range. So this is the explanation of this particular diagram. Now next one is the FHSS transmitter, and this is the FHSS receiver. In this particular transmitter we are having an MT, which is an input signal applied to a channel coding, and output of this particular channel coding will be a 1-bit data. This particular 1 bit of data is applied as to a digital frequency synthesizer, and we require to apply the PN sequence code. Now this PN sequence code is variable in nature. It is of higher number of bits. It is having higher number of bits. Now it is applied to this local oscillator, to this frequency multiplier, which is of k number of bits. So this is the FHSS transmitter. Next one is the FHSS receiver. Now at this this is the receiving antenna. Whatever signal you have received, it is first applied to a mixer. To this particular mixer, we require to apply the PN sequences, which is been generated after a PN code generated. It is passed through a digital frequency synthesizer, then it is passed through a frequency multiplier. Output of this mixer will be a BFSK code, BFSK signal, that is the binary frequency shift keying. Then it is passed through this error correction, and then M-T. Now M-T is nothing, it is the approximation of the input signal. So MT will be the input signal and M-T will be the approximated signal. Now this is the data and time frequency plane. You can see over here, like this is the control codes, which is of different bits. Now this is the carrier frequency, which is of 8 kilohertz. Different frequency ranges are there. Now this is the derivation of the output frequency. Now you can see that a variable value will be added to this one and subtracted also. So this will be the output frequency that you have generated after this particular calculation. So you can see that it will going to, the signal will going to modulate in this frequency band, this frequency band, then this frequency band. Likewise, this is known as frequency hopping. It will going to hop from one frequency band to another frequency band. Now next is the time hopping spread spectrum. Now in this case, as in the previous one, there will be hopping from one frequency to another. Then in this case, it will hop from one time duration to another time duration. Now this is the one frame. You can see that different slots will be there. Second frame, this will be the second one, third one and fourth one, and the particular data will going to hop from one time slot to another time slot, then third one and fourth one. So this is the different time intervals are there. So this is the time hopping SS system. Now you can see that this will be the input data, this will be the spreading pulse, which will going to modulate from one particular point to another particular point. So this is the another data will be there. So in the typical time hopping signal, it is divided into frames, which turns subdivided into m number of time slots. So as the message is transmitted, only one time slot in the frame is modulated with the information. Then the time slot is chosen using the PN generator. All of the messages bits are gathered together in the previous frame, and then they are transmitted in the first during the time slot selected by the PN generator. So if we are going to consider TF, that is the frame duration, K will be the number of message bits in one frame. So TF will be equals to K star into TM, that is then the width of each time slot in a frame is given by TF by M, and the width of each bit in the time slot is given by TF by KM, or just the TM by M. So this is how the bits will be generated. Now this is the diagram showing how the time hopping system will work. This is the on off switch which will be applied as an input. To this input will be applied. Then there at the receiver side, the demodulation unit will be there. So this is basically the demodulation of the THSS system. Then the bit synchronization will be there. Here the storage and retiming time will be there. So this is how the THSS system will work. Now this table is showing the difference between the DS, FH and the TH system. as it is mentioned in the previous slide, that DS system belongs to this averaging time, and FH and TH belongs to this avoidance time. This is used for this log acquisition system, this is used for this short, and likewise this is used for log acquisition system. These are the advantages and limitations of the different models are there. Last one is the hybrid spectrum technique, which is the combination which basically going to combine the advantages of the different systems. So the use of this hybrid technique attempt to capitalize upon the advantage of a particular method while avoiding the disadvantage. The PN generators are easy to implement, and spreading operation itself can be simplified, performed by the XOR ports. So selection of this SFH or FFH also has its own pros and cons, and solution will be, we are going to use this PN sequence, frequency hopping, PN sequence time hopping, frequency hopping, time hopping, and combination of all the three. So these are the hybrid combinations that can be possible, which will going to combine the advantage of FH, TH and PN. So this is how the data will be generated. This is carrier 1, carrier 2 and 4 carriers are there. So this is the PN code for 1, PN code for 2nd, PN code for 3rd, PN code for 4th. So this is how the code will be generated. It will going to hop in frequency and time both. Now last one is the application of SS modulation. The specific example of use of this SS technology is in the North America code, CDMA code it will be used. That is, CDMA is also known as IS95. CDMA in the standard uses a spread spectrum signal with 1.23 megahertz of spreading bandwidth. The standard also recommends use of forward error correction coding with interleaving speech activity detection and variable rate speech encoding. The spread signal is sent over the ear interface with QPSK modulation with root raised cosine pulse shaping, that is denoted by RRC pulse shaping. So in this lecture we have discussed about SS and different types of SS that exist. Thank you.